Welcome to Circuit Fix. I was clicking around YouTube this morning when I ran across an old video I made years ago about my grandfather's old Fender VibroChamp amplifier. I recorded that video in this very room when all I had in here were a few folding tables and some rudimentary tools like the iPhone 5 I probably used as a camera. Anyway, I thought I would repost that old video here and I hope you enjoy.
This is my grandfather's early Silverface Fender VibroChamp amp. Around 1987 I got a hold of this thing and it was in excellent condition. Sometime in the early 1990s this thing self-destructed. It was red plating the tubes, the vibrato was shot, and the thing was shocking me every time I plugged into it.
I'm shocked.
Eventually it stopped working completely, at which point my parents took the amp to some General Electronics repair shop in Gulfport, Mississippi. After waiting several weeks for the repair to be done, we got the amp back in semi-operational condition. After all that work, the amp sounds thin and distorted.
Listen, if I wasn't involved, this it would burn to the
The vibrato channel has no effect, the output tube is still running hot, and they've replaced the original Jensen speaker with something from Radio Shack. Saying it out loud makes me more angry now than it did back then. Sometime shortly after that, I opened the amp up myself to have a look inside. I'm not sure how well a 14-year-old can read schematics, but I could tell that there are cheap Chinese parts on the inside, and there were some things missing that were on the schematic, but not present in the circuit. Now this beauty has been sitting in my basement for around 20 years. During its long tenure with feral cats, dust bunnies, and mice, I've been doing the best I can to learn about how these tube amplifiers work. I have an idea or two about how to get this jewel working properly again. The first order of business is probably to do something about this original power cord. I think its usefulness is at an end and it's time for a replacement. Now with the chassis removed and upside down, we can see the power transformer, filter cap can, and the output transformer. The code visible on the power supply reads 606737. This code means it was manufactured by Schumacher on the 37th week of 1967. VibroChamp circuit AA764, and the transformer showed it to be 1967 37th week. The first thing I notice is the death cap needs deletion, and the primary of the transformer needs to be rewired. Two-prong original power cord, and it's toast, as we've seen earlier. The Mallory cap can shows obvious problems, so I'm going to order a replacement rather than stuff electrolytic caps somewhere randomly in the chassis. So I've replaced this old power cord even though it still may have a few years of life left in it. In its place, I've installed a brand new modern 3-prong power cord. I've used the original strain relief, but I had to cut the wire down a bit and use a zip tie to hold it in place. After I've pulled out this old crap, I've run the hot lead of the new power cable to the fuse holder, from the fuse holder to the power switch, and from the power switch to the power transformer primary. Emerging from the second side of the primary of the power transformer, we solder and shrink wrap to the neutral white wire, returning to the mains power. After removing the death cap, I ran the ground wire through the chassis where the death cap used to be, and soldered it firmly to the chassis where that pesky death cap once resided. Now I've discovered that the original fuse holder is also garbage, so out it goes and in with the new. Now, I've already begun testing and replacing some of these components, like the capacitors and resistors in the circuit that have been causing us problems. All of the 25-volt electrolytic Mallory capacitors were bad. I've replaced them with Sprague atoms. I've turned my attention towards resurrecting that old vibrato circuit. These 3 capacitors did not test well in the circuit, so I have replaced them with orange drops. These capacitors are absolutely crucial to the function of the vibrato circuit, and here's why. The vibrato circuit is handled by the second 12AX7 vacuum tube, designated on the schematic as V2. The .022 and the 2.001 microfarad caps properly configured in the circuit with the 1 meg resistor to ground and the grid of the first side of V2. This is a series of 3 high-pass filters. This creates the proper phase shift for the oscillator circuit to send downstream to the screen grid of the 6V6 output tube. I'm now considering the vibrato repaired, and we can move on to something else. Some of the problems within this amp could be caused by dirty potentiometers or tube sockets. Here I'm cleaning the potentiometers with alcohol-based spray and finishing up with a spray lubrication. Here I'm cleaning the tube sockets with the same alcohol-based spray. Now I've brought the amp up slowly on a variac to allow the new capacitors to form, and with the variac plugged into the current limiter, I can tell with the bulb glowing slightly that the amp is pulling more current than it should. Now I will check the bias on the output tube. I won't be surprised to see it running hot. The first step in this process is to measure the cathode bias resistor. Now we write this value down, power up the circuit, and check the voltage drop across the resistor. The final piece of information we need is the plate voltage of the output tube. This plate voltage is insanely high. Let's see if we can find out why. Here I've connected my DC voltmeter to the output of the rectifier tube. It shows a whopping 481 volts on the B+ rail. Here I'm testing both sides of the full wave rectifier tube, which is a 5Y3 GT. This is the tungsten tube that was in the amp. As we can see, it's pegging the meter on both tests. Let's see if I can find another tube that isn't quite so energetic to bring down that B+ voltage. Here's an old Sylvania 5Y3 GT that I found in my parts box. Here we can see it's testing much lower than that original tungsten. Let's try it in the circuit and see if it brings down that dangerous DC. I've discovered the settings on the variac cannot be trusted, although I'm not quite sure why that would be. I'll be testing the AC supply voltage now with a meter, and I'll bring it down to an appropriate level. With the voltage from the variac tamed and the rectifier replaced, we now see a much more appropriate B+ voltage for the circuit. After we've brought the amp back up to voltage slowly on the variac, the positive DC voltage on the B+ seems to be more under control. Let's do some math to find out the plate dissipation of this tube. Using a variation of Ohm's law, voltage drop divided by resistance equals amperage, we can compute plate dissipation. Our measured voltage drop across the resistor was 26.1 volts. We measured the resistor at 474.7 ohms. Using our trusty Casio calculator, we divide 26.1 by 474.7 to get 0.05498 amps. Move the decimal place over 3 spots, and that gives us 54.98 milliamps. After making adjustments to the variac, our new plate voltage is 407.5 volts. Plate dissipation is determined by multiplying plate voltage by plate current in full amps. In this case, our result is 22.4 watts. This is almost double the rating of a normal 6V6 output tube. To begin this process, I take a 1 ohm resistor and place it in line with some clips and discharge the filter caps so I don't get shocked. I don't care for this hot biasing. The 470 ohm stock resistor just won't do. Let's change out this resistor with a 5-watt 1K and see what happens. Now I use a set of pliers and my soldering iron to completely remove the old component from the eyelet board. Now I'll cut and bend the leads of the new part and put it into place. With the new cathode resistor in place, using the same process as before, I'm going to check the bias of the output tube once again. Now with our new 1K resistor installed with a 30.53 voltage drop across it, with a 400 volt plate current, that gives us 12.44 watts.
That'll do, pig.
At this point I want to try and see if the amp will pass any signal. Let's plug a guitar into it and see what happens. So I'm not passing signal properly through my preamp circuit, and the voltages are reading very high on the preamp tubes. So I see some things that are miswired. I don't know when this happened, but I'm going to take it all the way down to the board, make sure the wiring of the tube sockets and potentiometers matches the schematic, and then go from there. I've now restored the wiring of this amplifier to stock. Let's inject the test tone into the input and then follow the signal path on the scope. Here we can see the signal is already emerging from the first side of the 12AX7. Moving our probe to the plate of the second 12AX7 should reveal volume control. Now I need to tackle this loose board on the bottom. This could cause shorting within the components. I found some appropriate screws that will screw into the chassis. I'll put everything back into place as Leo Fender intended. Now to slide the chassis back into place and replace all 4 retaining screws and nuts. Now the speaker jack isn't fitting very well, so I'll tighten it up and reinstall it. It looks like there's supposed to be some sort of strain relief on the power cord here, so I'll dig through my collection and see what I have to replace it with. Okay. Now I can replace the back door and do a sound test. Now I've brought the amp into my living room and plugged it in for the sound test. This is the Tweed basement clone that I hand built, and a cabinet for a new project I'm working on right now. With no further ado, the Fender VibroChamp. So there we have my grandfather's old VibroChamp amp. Let me know what you think. Thanks for watching.
Circuit fixed.